So let us consider this waves and vibrations module. Let's consider a horizontal mass spring system below. Let's say that we placed a mass, a little block here, attached to a spring, and its starting point is x equals 0. Just call it that. That's going to be our equilibrium position. And let's say that we pull this block to the right. When we pull this block to the right, we're going to give it a certain distance from 0 that we call the amplitude. It's called the displacement, the amplitude. It just depends on your perspective. But in terms of the wave itself, and in terms of waves, period, in the basic context of talking about waves, we talk about the distance from 0 as the amplitude. So x equals A for amplitude. That's just the distance from 0, the distance from the starting point. There is a force that we call the restoring force, or the spring force, that is trying to bring this mass back to 0. And that, it's trying to restore the balance, trying to restore the original position. That's why we call it sometimes the restoring force. Right now, okay, so amplitude is the distance from 0. Remember, this is a spring, and this spring is trying to restore the mass back to 0. So Fs, I'll call it, for spring force. And we're going to call that, we're going to give a, quantify that spring force as negative K delta X. Now this delta X is the same as A. So, anytime you see delta X, it's just going to be equal to the amplitude. Delta X is the displacement from 0, or the amplitude. Fs is the spring force. K is what we call the spring constant. Every spring has its constant, or its amount of strength. Tightly wound springs have more K than a looser spring. It's just basically how strong your spring is. That's what K is. It's a spring constant. Or, you can just call it spring strength. Delta X is the displacement from 0. So you had x equals 0 first, and you go to x equals, say, 2. 2 minus 0 is your delta X. Displacement, which is the same as, your amplitude A. Okay, so now, after you've pulled this mass spring system to the right to an amplitude A and you let it go, what's going to happen is that this spring is going to go back through 0, and it's going to go onto the left side at negative A. It's going to be the same distance from 0 on the left and the right. The basic reason for that is because the spring force is going to be constant throughout the entire motion of this mass spring system. So this spring force is a constant force, and that's why it's going to cause it to go at positive A and then negative A as it goes through 0, right? So it's back and forth. You've seen pendulums before. You let it go, it just sways back and forth through the mg sine theta force. It's just driving it. In this case, it's going to be a spring force, back and forth. Pendulum, back, forth. Physical pendulum, back, forth. Torsional pendulum, back, forth. Because the spring force in all of those cases never changes. And so it's always going to be the same distance from 0, positive A and negative A. So in this case, we have positive A. Let's say this will be the first case. So we can even go ahead and say that if we want to get real nasty with it, theta is equal to 0 degrees. Okay, that's the first point on your unit circle. Then it goes through pi over 2. Then it goes to pi. Then it goes back to 3 pi over 2. Then back to 2 pi. That's a full period. You've seen that before in your math classes, I suspect. Right? Okay, well, basically what's happening, let me just, before I do the rest of that. So let's say that this is going to be a unit circle where the angles are in degrees. So this is be 0 degrees. That's our starting point. That'll be A right down there. And this is going to be, I'm going to put it in radians. So this would be pi over 2 or 90 degrees, pi. Then this is going to be 3 pi over 2. And then we're back to the start. That's going to be your 2 pi. You know that 2 pi, 6.28 radians, 360 degrees. You're familiar with that. It's a complete circle. It's a complete revolution, right? So in this picture down below, this is 0 degrees or at A. Then it subtends through from 0 all the way to pi over 2. It goes this way, and that's going to be at pi over 2. It's going to be at the midpoint, a quarter of the period. Then it's going to go half period. Then it's going to go 3/4 period, a full period. So the full period, so I'm talking about this word period, T is the time it takes to complete one cycle. This is one cycle, period of time T. And the amount of cycles in that period is what we call the frequency. They are inverses of each other, but I'll get to that in a moment. So this back and forth motion, and there's many types of back and forth motion in nature, we call periodic motion, just a motion of a mass spring system going back and forth, a motion of a pendulum going back and forth, the ebb and flow of your tide coming into the shore and going back out to the ocean, you leaving your house, going to school and back to your house. That's periodic motion, but there's a special type of periodic motion that is important to us. And that periodic motion is what we call simple harmonic motion. This is the motion that is, well, simple, it's harmonic, and it's motion. And the reason why we call it that, to distinguish it from all other types of periodic motion, is that simple harmonic motion deals with a force that's always trying to bring it back to balance. And that's what's happening in our mass spring system and our pendulums, for example. So let me just go ahead and define that. Periodic motion. You know, I say regular motion, or is it regular motion through time, right? So it's just like, you know, going back through 0, back, forth is regular, you know. Just trying to make this, you know, English, regular motion through time. But there's a particular type of periodic motion that is important to us physicists, and that's the simple harmonic motion, the motion that involves a restoring force. So, simple harmonic motion is periodic motion that involves a restoring force. And our restoring force in this case is a spring force. It involves a restoring force. And in this case, that'll be Fs for our spring force. So even though you may leave your house and go to school and come back, that's not simple harmonic motion, because it doesn't happen in the same way. You may have different types of forces leaving your house and coming back from the school. It could be raining on the way back home. You have different types of friction in the road that you didn't have, different conditions in the road that you didn't have when you left the house for the day, or the tide in the ocean is not going to always get back to the same point every time. It's going to get approximately back. You know, there's low tide, there's high tide, so it varies. It's still periodic, but it's not simple harmonic. Simple harmonic motion is the motion that always involves some constant restoring force, like the mass spring system that we have, and pendulums, physical pendulums, torsional pendulums, even double pendulums. Those are more complex systems, all of that. So So let's go to the, say the next picture of this mass spring system, right? So now we were at A, and so now we're going to come back. So what I mean here is that this was at A, or 0 degrees. And then at the middle, it's going to come back at pi over 2. And then it's going to come over here at pi, and it's going to come over here at 3 pi over 2, and then 2 pi. One period. The period, the time between the time it takes to go from the start back to start, you know, or time it takes to complete one full cycle, right? So so then after it leaves A, it will be back here, x equals 0, and because it was coming from A, so this would be so this is A here, or 0 degrees, but now it's at x equals 0. That's the position, but in terms of the radians, that would be pi over 2. Then it continues on, and you're going to get something like this here. It's not to scale, but you get the idea. Okay, so this is going to be x equals negative A, okay, or theta is pi, right? So you can kind of see the pattern. It is very pattern based. All of it is. This mass spring system is the same mass spring system that you use in quantum mechanics, that you use in the musical instruments, that you use in a broadcast signal from a radio station. It's all the same physics. It's your perspective and how you're going to manipulate the wave changes. So the other little subtleties to it as well, but it's basically the same. So it's equals to 0. That's our restoring force. So once it's at the middle point, the restoring force is 0 because there's no displacement at the middle, right? X is 0. K times 0 is 0. And out here, the restoring force is going to go to the right because it's trying to pull you back to the right. No, you're going left. No, I want you to go right. Oh, you went right. No, I want you to go left. So it's always trying to get back to 0. That's why it's periodic. Back, it's forth, back, forth. So that's just pi. And then it goes back to 0. Okay, after leaving pi, or this point. So this is back to x equals 0, or theta equals 3 pi over 2, 270 degrees. And then at the end of the day, it goes back. I mean, once it gets back to where it started, that's one cycle, one period, one cycle, one wavelength. You know, get into all that. So now it's at positive A, and theta is 2 pi. 2 pi radians, one full cycle. The period is T. This is one wavelength. I'm just going to throw this in there. That's a W for wavelength and lambda. So the space traveled, the distance traveled by this wave in one period is the wavelength. So you can see that it all depends on each other. It's all married together. It's all part of the same thing. Is one wavelength of distance corresponds to one period of time, which is 2 pi radians, and the distance is A. Simple harmonic motion. It just bobs and weaves back and forth regularly under the power of one constant force. That is the distinction between regular periodic motion and simple harmonic motion. Questions thus far before we go forward? But that's the point I wanted to make. I wanted to do the example of the horizontal mass spring system. Yeah, we could have done the vertical. It's the same thing, except there's gravity in there. We can ignore the gravity because the gravity is not going to be part of the restoring force, because the gravity is always going to just be pointing downward. It's never going to be acting back towards zero. So, but in order to describe it holistically, we have to include gravity. But we keep it simple for now. Okay, so this spring force is also called Hooke's law, after Robert Hooke's, I think 1700s. So this spring force, negative K delta X, Hooke's law. Hooke's law is the restoring force, same. Of course, this is a vector, forces, K is a constant, this is a vector. And another thing, K is measured in force per meter, or not, Newton per meter, so delta X. So the units of the K are newtons per meter, because it's force divided by displacement. Okay, so, and there's a graph here in your ebook, in your textbook, that talks about the linearity between force and distance. Indeed, because this is going to be a slope, right? This is going to be rise over run, and it's going to give you that constant spring force. Because the spring will never change its properties on its own. It has to be heated up or mangled or frozen or something. But on its own, it's always going to have this spring force. It's constant. Never changes. And the more tightly wound springs, that's what you want to have in your shock absorbers in your car. You want that spring to be huge and very thick and wound up, because you have a car that's always bouncing on little bumps, you get sick. So you want it to just, bounce real hard and keep going. So that spring constant is very large. So spring force, Hooke's law, talking about potential energy and stuff. And it goes into talking about how, it's not really, this is an ideal situation that Hooke's law, for the most part, works in real life. But there are, types of springs like rubber bands that don't necessarily obey Hooke's law, because they can get stretched too easily past their elastic limit. But generally speaking, for our ideal situation, when we don't consider friction and we don't talk about the elastic limit of things, Hooke's law is obeyed. It's constant. So then there's the potential energy of a spring. Let's talk about that a little bit. Well, potential energy. So let's go, if we go back to this scenario here, okay, where now we're at the starting point. The potential energy of a spring, let's keep it simple, only exists at the edges. Because for a moment at the edge, the object does not move. Just like when we throw a ball in the air, for an instant at the top, its apex, it doesn't move, and then it comes back down. But it's instantaneous. So spring potential energy, works like that. So PES for spring potential energy, 1/2 K delta X squared. They have it as -1/2 K delta X squared. That's incorrect. because when you integrate force to get the energy, that minus sign goes away. But it's a minor issue there. Because I think they wrote it and hadn't really considered displacement properly. But yeah, in order to get there here, you can integrate the force to get this properly. It's going to be exact. 1/2 k delta x squared. So again, the spring energy only exists at the edges, as you can see, delta x, or which is the amplitude. You can also write this in some cases as 1/2 k a squared, because a is delta x. So the potential energy is only at the edges. Because that's where maximum displacement occurs. Well, okay, again, maximum potential energy is at the edges. You can have potential energy at any other place that's not zero, but we're going to keep it simple and talk about the maximum potential energy. So that's at the edges. And then once that potential energy, once the mass starts moving, all that potential energy gets converted to maximum kinetic energy at the middle. That's when it's moving the fastest, when x is equal to 0. And then it goes and converts it back to potential, to kinetic, potential, kinetic, potential, back and forth, under the influence of one constant force. And when you think about it even further, you can see that this works in our model of energy conservation. We had a ball up in the air. It moves back down. It goes from potential at the top to kinetic. What's the one force? What's the one force causing it to change from potential to kinetic? The force due to?
Gravity.
Gravity. That's right. So the force due to gravity, which is a constant force, is converting that potential energy to kinetic. And this is exactly what's going on here, except the difference here is that it's going to go back and forth under its own power, if you will. Once an object hits the ground, it's pretty much done. But if there was a situation where there was no friction once the ball hit the ground, it would go back to the top, back and forth. So that would be a type of simple harmonic motion. But unfortunately, we have friction, and so the bouncing of the ball off the ground is not simple harmonic. Irregular and periodic, it happens, but the height decreases exponentially until it comes to stop. But anyway, this is the spring potential energy. Good. And one last thing before I guess we do a sample problem is to talk about the math function associated with this spring energy. And you may have guessed it already. It's a sinusoidal function, or it's a sine or a cosine function. Because see, we have the concepts, we have the physics here, and now we want to predict the future. We want to assign a function that's going to allow us to figure out, well, what's the speed going to be at 2.7 seconds? Well, there's a particular function that allows us to do that, and that is our sinusoidal functions, our sine or cosine functions that we see in math. So that stuff is all going to come back. I mean, we're not going to do it directly, but that's the function that is associated with this. And thank you, Sophia, for your answer there. Yeah, so that, good. So let's take a look at the function assigned to that. So like we pull this mass to A, and it's positive A. We know already, or we may be able to infer, okay, draw a straight line here. We may be able to infer that the function associated with that positive A is going to be a cosine function. Because it starts at an amplitude, and then At pi over 2, cosine is equal to 0. At pi, it's -1, or in this case, negative a. And I say a can be anything. It can be 2, it can be 3,000, 200. But it's going to be a positive and negative a. And it never goes beyond those boundaries, not unless you push it in the middle of its motion. Once you let it go, it's going to go between plus and minus a. And you know that that goes back to your sine and cosine functions, that the sine and cosine function can never go past 1 or -1. Those are the boundaries. It's undefined after that. So then we take that math and put it to the physics here and see exactly that that applies directly. You can never go past positive and negative a. So it's positive a, and it comes down, and it goes up, and then comes back over here. Okay. So anyway, 3 pi over 2. Sorry about that. And then this will be 2 pi. As you can see here, it's stopped. Its starting point and its stopping point is the same. This distance is what is called a wavelength in that one period of time. See how it all starts to fit together? It definitely is a marriage between all of that good stuff. Okay, no problem, no problem. So, and look at it. So this is a cosine function. So this is going to be cosine theta, but, and we're not going to use this. This is mostly in our AP version, but I'm just going to write it here. So we can figure out where this object's going to be at any moment in time, where omega t is your theta. So this is the basic function associated with it. It's a cosine function, cosine theta, and a is its amplitude, back and forth. What's the position here at t equals whatever? And I can change this x-axis to times. I can figure that out. That function allows me to do that. Or in terms of radians, I can figure out. So if that's a not quite pi over 2, let's say that's pi over 3 or something, I can figure out what my position is, my coordinate. So that's what's happening here. Wave motion, mass spring system. And so Friday, we'll just do a couple of questions before I take you off to your Labster. But questions thus far, does anybody need to see anything? We do have some time. Maybe we will do a sample question. After cosine, oh, it's omega t. Again, you don't have to worry about this part. I was just giving you the function that governs this motion, or that you can use to describe this motion. It's all this really is just cosine. You have to use like a differential equation in order to get this final equation here. Well, that's one of the methods of deriving this equation. But anyway, maybe this will look a bit easier. So let's say they're in our unit circle. And the unit circle is basically periodic, okay? And this is angle theta. This distance we call our amplitude, our radius, the distance from 0. See, it goes all the way around. So if we're looking at the x-axis, this would be cosine. X is equal to a cosine theta. Why is that? Because cosine theta is adjacent over hypotenuse. So this is going to be x divided by a. So this is x, right? And this will be our arc length that we can call r theta, but delta theta, which is omega t. But yeah, we're not going to worry about arc length in this context. Keep it more simple than that. Cosine theta is adjacent leg over hypotenuse. And then if we just want to solve for x, it would be a cosine theta. And in terms of rotational motion, theta is an angular position, very similar to x in a linear position. But then if we were looking between this position and another position, it'd be an angular displacement, delta theta. But anyway, this just converts to omega times time, because remember that x is equal to velocity times time. Well, angular position is angular velocity times time. That's why we get this. So that's the basic reason. That's the basic look as to where that equation comes from. Then we can solve for it by using force, but then we have to use a differential equation to get to that point. It's, it just depends on where you're approaching the problem from. But that's what it is. Omega t, a cosine omega t is that. Again, we won't be using the sine function in order to figure out what things are. I'm just giving you the broad picture. Okay, so there's all of that. So yeah, S, R theta, S is R theta. So now, then once you start traveling, you can get the delta S, the change in arc length that will allow you to get the angular velocity. And then after that, if you change the angular velocity, you can get the angular acceleration. But that's just going off, on the tangent, the deep end over there. So we don't want to confuse it. Yeah, so that's periodic motion. We're going to be using mass spring, the spring force. Let's do a sample question before we're out of here. Page 341 of your text. We're going to go to additional practice right in the middle. Page 341, page 108 of the ebook. So these should be hopefully okay. Okay, the first question. What is the spring constant of a spring that stretches 12 centimeters when an object weighing 24 newtons is hung from it? Okay, so now they're doing the vertical mass spring system. We get horizontal, same. So F is equal to negative K delta X. So even though there's weight going this way, and it's still, the spring force is going to be equal and opposite the other way. So spring force is this weight. Okay, 24. So what we have here is a situation where, let's say 0 is somewhere up here. We have the spring force. No, I want you to come back. And gravity is like, no, come back down. This is, and it's static. So Fs is equal to Fg, or the weight, 24. And the distance is 0.12 meters, 12 centimeters. And solve for the spring constant, just divide force over displacement. And the force is 24 newtons over 0.12 meters. (200 newtons per meter). Okay, questions on that? Remember, this is a vector. That's a vector. So in talking about musical instruments, like for instance, this wave over here to the left, what happens when we place our fingers on the strings in the different ways, we're taking that standing wave and we're modifying it. So now when we do that, the wave just looks different now. It goes from say one hump, from start to finish, to 2 or 3, depending on where we place our fingers. And as we do that, that changes the pitch of the string itself, the sound. So it's all music is the superposition of any event of all things of an almost innumerable amount of possibilities of pitches. It's not innumerable, but all of those, whatever the number is, we're accessing all those possibilities to make chords, to make notes, songs, all that. So it's just this blending of all of these possibilities and all of those strings, and we're accessing them. The more prolific, the better we are as a musician. We have greater facility to access those possibilities because we know how to play. That's the kind of thing. But it's beautiful. I like this topic, and hope you guys will, have some enjoyment out of that, because we're doing this. The musical project is that's how we're going to end off the year. It's going to be doing physics of all the orchestral instruments. Well, not all the strings. Start with the guitar. Start with the electric bass, electric guitar. Then we'll do violin. Then we'll do violas, cellos. Yeah, maybe upright bass, but once we do the electric bass, it's the same thing. It's tricky when we do the winds because you can get the distance that the notes are produced at, but then now translating that to the holes in the trumpet or flutes. Just think about it, it's a little hard to see. But we'll be able to do the strings relatively easily. Okay, right? So that's number 1. Let's try number 2 here, and then we'll be done. So it says, what is the elastic potential energy of a spring with K equals 144 newtons per meter that is compressed by 16.5 centimeters, right? So we're looking for a spring energy. You have the spring constant. Make sure you convert centimeters to meters, and you got your answer. By the way, I'll have a slot for these notes, the whole the business. So 144 newtons per meter, and do 0.165 squared. You guys get 1.96 joules. So this is energy. Anybody else out there get that? Oops. I make a J. Does that make sense? 1/2 K 144.165 squared.
Yes, very straightforward.
Good. Yeah. Yep. Yeah. So this is you know, pretty easy. Hope you find that. So that's gonna do it for today. So next time, Friday, we'll do Labster. So it's like a spring force lab. So I just want to introduce the concept here, and then you guys can go off and do the Labster Friday. Next week, we'll do a little bit more on springs, and then we'll do a second Labster lab the following Friday. And then as some of you are coming in, I know that it's like Miles, Pierre, Edgar, and Mark are going to come in, right? You guys want to be there. I suppose. That's what I see here on the attendance. Okay, so as you guys are coming in, there's gonna be some people. The rest of you will be here. We're just gonna do the musical instruments. Just have fun, you know. You might as well try and make it as easy as the rest of the year, and don't bog yourself down as we are trying to resurrect the rest of the year. Okay. So that is it on that.